Hi everyone, thank you for joining us for lab exercise 2.2 where we're going to go over cellular membranes and transport across a cell. If we look at the materials list, we're going to be using 2 eggs, 3 cups, corn syrup, distilled water, a triple beam balance, a plastic spoon, and we're also going to use our smartphone today. So we are going to be going over diffusion, osmosis, and tonicity in the context of Brownian motion. We're also going to compare conditions that affect the rate of diffusion, and we're going to observe osmosis through a semi-permeable membrane using the egg as a model. Then we need to identify isotonic, hypotonic, and hypertonic solutions. So this pre-lab states that the egg has a semi-permeable membrane. That means some things are allowed to cross while others are not. For instance, water is not able to cross a phospholipid bilayer, but water can cross a semi-permeable membrane due to the fact that most membranes have something called aquaporins, and those aquaporins allow water to cross easily. This says your teacher has soaked eggs in vinegar. This dissolves the hard shell and leaves the soft outer membrane. This acts like the semi-permeable cell membrane of an animal cell. Number 1 says take one of the 8-ounce cups and label it distilled water. So we have one 8-ounce cup and we're going to label it distilled water using our lab marker, okay? And then number 1A says measure its mass on the triple beam balance. So I have my triple beam balance right here and it is at 0 at the moment. No mass. I'm going to put the cup here and I'm going to move the 10 gram. It's not quite enough. So it looks like 11 grams is about perfect. So I'm just gonna on the side here write 11 grams so that I can keep a note that the cup weighs about 11 grams. Number 2 says one group member needs to take 1 egg from the soaking container, gently rinse under the tap and pat dry. Note any visual or physical characteristics, the fullness, the shape, and the size. I have already taken them out of the soaking solution and rinsed them off and patted them dry. Now, what I can tell you is that these eggs are soft and slightly squishy because this membrane or the calcium has been rubbed off of it. So what I'm going to do is gently place this inside of my cup. And now I'm going to get the mass of both the cup and the egg together. So I know that the cup by itself weighs 11 or has a mass of 11 grams. So I'm going to start over at 0. Okay, so 100 was too much, so we're going to use the 10. All right, 70 was too much, so we're going to go back to 60, and then we're going to use the grams. So it looks like 68 grams for both the egg and the cup together. So I'm going to write that down. And I'm going to subtract the mass of the cup. And so the total mass of my egg is 57 grams. Okay, so that's my egg. It says the cup's mass must be subtracted from the mass of the egg. We did that already. And then it says record the mass on the table in the correct data section on page 4. So I am going to remember my egg was 57 grams, and I'm going to come to the back. Here under distilled water, my starting mass in grams is 57 grams. Next, it says, gently fill the cup with distilled water so that the egg is covered about 3/4 of the way full and put to the side. So I am going to take my distilled water and fill this with distilled water. It does take a minute. So we will set that to the side. It needs to be filled about 3/4 of the way, covering the egg. So I'm going to set this aside. Next, it says repeat steps 1 through 5. It should be 1 through 4. Complete steps 1 through 4 with corn syrup instead of distilled water. So I'm going to take my cup, measure the mass, which should be very similar, which is 11 grams. And then I'm going to add another egg and find the total mass. So I'm just going to use the last one as a guide. It should be about 68, and in fact it is 60. We got 68.5. 68.5 is perfect. So I'm going to do the same math problem. I'm going to take 68.5 grams and subtract 11 grams, and I am going to get 57.5 grams. So my second egg weighs 57.5 grams. So I'm going to go to the back and I'm going to enter under corn syrup, the beginning or the starting mass is 57.5 grams. Now I'm going to fill this container with corn syrup and set it aside. Okay, the longer that those soak in solution, the better. So I have one soaking in distilled water and one soaking in corn syrup. Down at the bottom, number 6 says set aside the 2 cups so they are out of the way, and we will return to this experiment at the end of class. Stir the corn syrup solution occasionally without disturbing the egg. So we just need to make sure to stir that corn syrup every once in a while. Now, you on your own can make a prediction. There is no wrong answer, but I want you to predict, what do you think will happen to the egg that's soaking in corn syrup? And what do you think will happen to the egg in the distilled water? Remember what you learned in lecture about these types of solutions. This solution has a ton of sugar in it, and this solution, distilled water, doesn't have anything in it at all. It's just water. So make your predictions, write that down, and then we will continue on to the next page. This page says, scan the QR code and click states to complete the activity below. So what we're going to do is we're going to be observing Brownie in motion, and you are going to scan this QR code. I have it pulled up on the computer over here so that we can work on it together. So when you get to this section, you should see on your phone something like this, where it's talking about states of matter. We're going to click states. Okay, so on our notes, it said press water and liquid. Currently, your water molecules are at room temperature. So let's go ahead and click water. So over here, we're looking at neon. We want to be looking at water, and we want to look at water as a liquid. So what I notice about water as a liquid is that it's all kind of pushed down to the bottom of the container. They're moving around and bumping into each other, but they don't have enough energy to escape gravity, and they don't really have, they have enough energy to be separated. So this is what the liquid water looks like at room temperature. A says, what happens when you lower the temperature of the water? So right here, what I'm going to do is I'm going to take this and I'm going to cool it down. So I'm seeing them expand a little bit. And as I'm dropping the temperature, they don't move around as much. They're still moving around, but they're not moving around very much. Okay, so write something to that effect in section A. What happens when you lower the temperature of the water? So the things that we observed when we lowered the temperature of the water was that the movement or the energy in these cells started to slow down. They're still moving though, they're still vibrating a little bit. You can especially see it right here. They are still moving, they're just not moving very much. The other thing that I notice is that they are all oriented towards each other, to where these hydrogens are pointing towards the other's oxygen, and that caused them to create these gaps because of those hydrogen bonds. B says, what happens when you raise the temperature of the water? So let's do that. We're going to take this and we're going to heat it up. Now all that energy, all that heat gets transferred into energy, and they start moving around. They're moving around so much that they're escaping gravity. All right, so we're filling the entire container, and the water is spinning and it's moving and bumping around very quickly. So when we're talking about what happens to the water when we raise the temperature, we've added energy to that system, and now they're bumping around and moving around like crazy, and they're filling the entire container. This paragraph says the energy of Brownian motion is directly related to the temperature of the matter you are observing. So Brownian motion is this random motion of these different molecules. When we increase the temperature, we are increasing the Brownian motion, or the energy at which these molecules are bouncing around and bumping into each other. So a gaseous state like this has the most energy, whereas if we lowered the energy or lowered the temperature, they would still be moving a little bit, but not very much. That means that it has less Brownian motion. Number 2 states, finish filling in the above diagram by drawing the molecules and arrows for how much energy a liquid and a solid would have. So these are just our gas molecules here, and the artist has drawn them very far apart. They're filling up the entire container, and this arrow represents having lots of energy. They're bouncing around a whole lot. That is similar to this phase, the gas phase. So I'm actually going to look at a different molecule like neon, and when I'm looking at neon as a gas, they're bumping around quite a bit. When I look at neon as a liquid, it all fills up the bottom of the container, and they're still moving around quite a lot, but not enough to really escape gravity. So when I'm drawing a liquid, I'm going to draw all my little molecules down at the bottom. Okay, you don't have to be an artist, but all these molecules should be down at the bottom, and they should have arrows representing that they have energy, but draw the arrows shorter than these, because this means it has lots of energy, and this means it has like maybe a medium amount of energy. And I'm sorry, I'm trying to draw while holding the phone, which is, not super efficient. So something like this. Next, it's asking you to draw a solid. So when I click phase change to a solid, you notice that these neon particles are very, very, very tightly packed together in a nice little cube. Okay, they're gathered together. They're still vibrating. They still have Brownian motion, but just not very much. So when I'm drawing a solid, I'm going to draw them very closely, tightly packed together. And gravity does affect them, so they're down towards the bottom of the box. Now, I want to represent that vibrating motion, so I'm going to draw these little parentheses, because to me that represents vibration. You could draw little arrows, but the arrows would need to be even smaller than the liquid. So we completed number 2. Number 3 says observe neon as a solid. Then switch your model to observe water as a solid. What is the difference between water and neon as solids? What property of water is this physical phenomenon lead to? So let's talk about water in particular as a solid. This is neon as a solid, and we can see that they're very, very tightly packed together. If I had a solid cube of neon and I dropped it inside a liquid vat of neon, that cube, that solid, would sink to the bottom. Because the solid, the molecules are much tightly packed together, or much more tightly packed together. They are more dense than the liquid state. But if I switch to water, the liquid state is actually more dense than the solid state. You notice that in the solid state, water has all these air bubbles in it. And that is because of those hydrogen bonds. The water creates these hydrogen bonds and actually expands when it freezes. So if I have a solid piece of water, such as an ice cube, and I drop it in liquid water, it will actually float because it is less dense than the liquid form. So on number 3, it's asking you what is the difference? Well, neon as a solid is very dense, whereas water as a solid is less dense than its liquid, and the property is that ice floats. This is due to hydrogen bonds. Number 4, Susie and Janice are trying to make tea. They both have 1 gallon of water and 1 bag of tea. Susie puts her gallon of water in the fridge because she likes her tea to be cold. Janice, however, boils her water first. Who will have an easier time diffusing the tea, and why? The obvious answer is that Janice will, because Janice heats her water up. We know this from experience because, most people know how to make tea. Not everyone, but most people. And in the South, Southern sweet tea is pretty widely known. We like to drink it cold, but we heat it up when we're making it so that we can dissolve the sugar and diffuse the tea very easily. So Janice definitely has an easier time, but why? Let's go back to our key word, Brownian motion here. Brownian motion. When we heat up that liquid, we're giving it more energy and it's bouncing around more. So diffusion will happen faster. I want you on your own to read this paragraph about tonicity. Look at the word hypotonic and what it means. Isotonic and hypertonic. Then we're going to answer questions 1, 2, 3, and 4, and I want you to reference where you found the answer. So, in number 1, in a hydroponic garden where plants are grown without soil and receive their nutrients from a water-based solution, how does the tonicity of the nutrient solution impact the health and growth of the plant? So first we need to identify, is this a hypertonic, isotonic, or hypotonic solution? Well, since the water has more water than solutes, than the cell, this is a lower solute concentration, hypotonic solution. So in number 1, a hypotonic solution, how is that going to affect our cells? So let's look at our paragraph for hypotonic. It says that this can cause animal cells to swell and rupture. This is called lysis, okay? This is really bad for animal cells because the water will force its way into the cell because there's way more water outside the cell than inside the cell. But it says plants will thrive, okay? So how will it affect your plants? They will thrive, and that's because plants have a cell wall. They don't just have a cell membrane, they have a cell wall, and they have a large central vacuole, and the vacuole needs to put pressure on this wall in order for the plant to stand up straight. This is called turgor. So your answer needs to say something about turgor and something about hypotonic. Number 2, in the context of food preservation, how does the concept of tonicity play a role in methods like pickling or salting? So when I am pickling or salting a food, I'm putting it in a solution that has lots and lots of solutes, particularly salt, lots and lots of salt, to draw the water out of the food. This is a hypertonic solution, okay? And it says that for animal cells, this is going to create crenation or cell shrinkage because the water is pulled out. So this is a hypertonic solution, hyper meaning above, way more solutes in this kind of solution. And it's going to cause our cells to shrink because the water leaves the cells. This is a great way to preserve food. This is how you make salted meats or pickling. If you put a cucumber inside of a pickling solution, the water is pulled out of the cucumber and replacing it is the salt brine. All right, number 3, when a patient is receiving an IV, we want to make sure that the fluids are safe for the patient. So we really should probably choose an isotonic solution. Iso meaning same. That way, when our cells, or particularly our blood cells, come in contact with the solution, the same amount of water enters as exits the cell. So we have no net movement of water. There are different cases, depending on the medical condition that they're being treated for, that they would use different types of IV fluids. If a patient is dehydrated, we might want to use a very slightly hypotonic solution just to rehydrate that patient, but overwhelmingly, we're gonna wanna use an isotonic solution. Number 4 says, do you think it's a good idea to drink distilled water? Well, probably not, because distilled water is not isotonic. It's actually hypotonic, and the hypotonic solution can cause cell lysis. We don't want that. Even though plants do well with it, animal cells do not. So the answer would be no, and I need you to tell me why. The next step is called transport across a membrane. There are 3 challenges that we need to complete, but first you need to scan the QR code to be able to get to the interactive. I already have it pulled up on the computer, so we can do this interactive together when it decides to load. Okay, when I'm beginning this interactive, I'm going to click Accept Challenge. There are 3 challenges listed on your paper. They are the exact same challenges that are listed on this simulation. So the first challenge is using active transport, make the extracellular solution hypertonic. So this blue area is the outside of the cell and the yellow area is the inside of the cell. What this says is we want the extracellular solution, the blue area, to be hypertonic. Hyper means above. So we want more blue outside the cell than inside. So right now it says that I am isotonic. That's what it's telling me. So I need, in order to move on to the next challenge, I need to get all of these blue particles outside of the cell. Right now what I notice is that they're able to cross the cell membrane very, very easily because they're really big, or they're really small. So I'm going to come over here and I'm going to make them larger. That way they can't cross the membrane. So now the only thing able to cross this membrane are the red particles. But I'm still rather isotonic. I need to get these blue particles outside of the cell. So I'm going to add a transport or a uniporter. This is active transport. It has to use energy. I'm only focused on the blue particles, and I want the blue particles to leave the cell. So I'm going to click this a few times to make sure that I'm adding transport that will leave the cell. So this is what it did. It added 3 uniporters, and they're using active transport ATP to move these blue particles out of the cell. So now you can see my cell is mildly hypertonic. All I have to do is wait. If I want to speed up the process, I can add energy to the system by increasing the temperature. So now these particles are moving way faster. They've increased their Brownian motion. It gave me a check, so I can move on to the next challenge. Now, this challenge says make a solution that both red and blue molecules are isotonic. I could use active transport, but the active transport forcefully moves particles from one side to another. I don't really want that. I want them to be able to move freely. But these particles are too big to cross the membrane. So what I'm going to do is I'm actually going to make both of them really tiny so they can actively move or passively move across the membrane. So now they can passively move, and I do have a mildly hypertonic and mildly hypotonic side, but I want both of them to be isotonic, and it seems like it worked pretty well, pretty quickly. I'm going to increase the temperature so that this happens a little faster. Now I'm allowed to click the next challenge. This challenge states I want to create a solution that is isotonic for blue molecules. I know how to do that. So first thing I need to do is add some blue molecules. So I'm going to come here and I'm going to type 100. And I'm going to add a bunch of blue molecules. These molecules are very large though, so I need to make them small. Now I want to see if I can get this to be isotonic. All right, so this is going to give me a check mark, isotonic. What's the second half of my challenge? I need it to be hypertonic, intracellular for red molecules. So that means I want more hyper inside, intracellular. So I want all the red to be over here. So I am going to add 100 red molecules. Actually, it's already done right here, so I need to add 100 red molecules. Now, these red molecules are too small. They can cross the membrane however they want to, leading to an isotonic solution. So I want to make these big so they can no longer cross. And now I need a way for them to enter into the cell. They're too big to enter into the cell, and I want the inside of the cell to be red. So I am going to add some uniporters. I'm going to add red uniporters, and I want them to face inside the cell. So I'm going to add some of these. So what this did was it added some uniporters going this direction. And if you're impatient and you want it to keep going faster, we can increase the temperature. Now we should see, just give it some time. All right, both are checked and we are done with the challenge. Done with the challenge. And that will start the simulation over. So let's answer some of our questions on the bottom here. We completed challenge 1. We completed challenge 2, and we completed challenge 3. Number 1 says, based on your experience in the simulation, how does changing the temperature affect diffusion? So, one way that it affected diffusion was that it added energy to the system, particularly added Brownian motion. So your answer should say something about adding energy or increasing Brownian motion. What other factors affected the rate of diffusion? Well, how many particles there were, and then how big the particles were also affected the rate of diffusion. Number 2 says, in the case of making extracellular fluid hypertonic with respect to one of the molecules, which 2 features of the membrane were important to establish? Well, one feature was that in order to make it hypertonic, I had to use some sort of active transport. And in this case, we used uniporters. And we had to make the molecules big enough to not be able to cross unless they were using those transporters. So in number 2, we need to say something about using active transport and the molecules not being able to cross the membrane. Number 3 says, which type of transport did we use to get an isotonic solution? And that would be passive transport. So the first half of this question is asking about passive transport. We let those molecules cross the membrane by themselves at random. Then it's asking about a hypertonic solution. In order to get a hypertonic solution, we had to use active transport, which uses ATP. We are done with these sections, so let's go to the back of the page. We need to complete our egg osmosis lab. Our eggs have been soaking for a while now, and it says, 1, take the egg gently out of the soaking cup, rinse gently under the tap water, pat dry, and place in a dry cup. A says, measure the ending mass of the egg by subtracting the mass of the cup. Then we need to record the mass in the table and repeat for both eggs. So let's do step 1 right now. I have my dry cup, and I need to get the mass of my dry cup. Well, I got 2 cups. I need to get the mass of my dry cup, which from experience I know should be around 11 grams. And what do you know? It is just about 11 grams. So I'm going to write down my notes, 11 grams for the cup. Okay? Next, I'm going to take my eggs that have been soaking. I have this egg that's been soaking in corn syrup and this egg that's been soaking in distilled water. I'm gonna do distilled water first because it's not as difficult for me with one hand. And I want you to make observations while we're doing this. This is an easy experiment that you can do at home, just using eggs and vinegar. You can use tap water instead of distilled water, and you can use pretty much any kind of syrup for the corn syrup. So what I notice about this egg is that it's very round and it's very squishy, okay? But before messing with it too much, I'm going to go ahead and measure it. I'm measuring the mass. So my original mass was about 68. So I know that it has gained mass because 68 is not even near it. We're gonna try to go to 70. Okay, so it looks like 70 is pretty close. Maybe 80. Going back, let's put it at 80. Ooh, 80 is good. All right, we've got 81.4. So I should have 81.4 grams for the egg and cup. So what I'm going to do is I'm going to subtract 11. I should have put the 11 underneath it, but this is easy enough to do in our head. So we've got 0.4 grams, and 1 minus 1 is 0, and 8 minus 1 is 70. So my egg by itself is now 70.4 grams. This is the distilled water egg, is now 70.4 grams at the end of my experiment. Now I need to do the corn syrup. The corn syrup is a little bit more messy. I'm gonna set this to the side. The corn syrup is a little bit more messy, and it's important that we don't pour this corn syrup down the sink because it can cause clogs. So I am going to kind of fish it out of there, and we can use our spoon if you want to. I just forgot that I had a spoon here. And I am going to gently rinse it, very gently rinse it. I don't want to pop the egg, so I'm only going to turn the water on a little bit, and I'm going to kind of use this cup to help me rinse it. All I'm doing is making sure that this egg doesn't have any syrup on it because I don't want to measure the syrup. All right, so now when I'm looking at this egg is also very squishy, but it's not as bouncy as this egg. And we can actually see the difference. This is the distilled water egg. It's very bouncy, whereas this one is not, and it's much smaller and kind of squishy. So let's go ahead and measure this one. I'm gonna put it in my dry cup. I know my cup weighs 11 grams, and I started out with a 68 gram egg. And so it looks like, did I start out with I started out with a 57 gram egg. So I started out with 57 gram egg. So we know that it's gonna be already all right, so what I have is 68.7 grams for the cup and egg. And then I'm going to subtract 11 grams for the cup. And I'm gonna pull my grams down. I've got 0.7, and my 8 minus 1 is 7. So I ended up with a net gain of 2 grams, but I will tell you right now that I cheated. I actually used a different egg than over here. So I didn't actually soak these eggs because I've been soaking these eggs all day. So what we should see is a net loss of water. We should see a net loss of water. So this one we errored. Okay, we should see a net loss of water, and I can tell from this one, like it's very small and very squishy, especially compared to the distilled water egg, which is much larger. Okay, I just measured a different egg, and all of these eggs are slightly different. All right, so the difference in mass, what I'm going to do is I'm going to subtract the ending number from the beginning number. And what we get if we subtract 70 from 57 from 70 is we are going to see a net gain, and here we're going to see a net loss. And here it looked like it was about 10 grams. Here we should also see not quite as much, it doesn't work quite as well, a net loss of maybe 5 grams. Okay, so what kind of solution is this? Well, distilled water has no solutes, so it is hypotonic. It has less solutes, whereas corn syrup is hypertonic. It has more solutes. So now we can answer number 5 and 6. What happened to the egg in the distilled water? Well, we can tell that it has swollen and absorbed water. Since water is the only thing that should be crossing this semi-permeable membrane, we know that it gained mass. And the mass that it gained is from water because it is a hypotonic solution. The water will force its way in. Now, what happened to the egg in the corn syrup? Well, it had a net loss of mass. It appears shriveled or smaller. And that is because it is a hypertonic solution. So the water is actually going to leave the cell. Down at the bottom, number 7 draw a picture of your eggs before and after. So in the distilled water, my egg was much larger and rounder afterwards. In the corn syrup, my egg was much smaller and kind of wrinkly afterwards. Okay, and this is an exaggeration of what happened. Number 8 says draw dots representing the solutes in the water. So in the distilled water, all of the dots should be inside of the egg. There are no solutes outside of the egg. At the end of the experiment, we should see kind of an equal number of dots inside and outside the egg. Actually, that's a lie, because I already said that the dots cannot cross the membrane. All right, in corn syrup, there are still solutes inside of the egg, but there are way more solutes outside of the egg. And it's all sugar, corn syrup. We still have all of these dots outside of the cell, but they're a little bit more spread out, and I'll explain why in a second. All right, number 8 said draw dots. Number 9 says draw arrows. We're going to draw arrows representing what happened to the water. So these are the solutes, okay? But the solutes cannot cross the membrane. The only thing that can cross the membrane is the water. So in order for the water to try to even out both sides, it is going to force its way through hydrostatic pressure, osmotic pressure, into the cell, causing it to swell. We're trying to dilute, or osmosis would try to move from an area of high water concentration to an area of low water concentration. Now in the corn syrup, the high water concentration is inside of the cell. There's much more water in this cell or in this egg than outside of it. So the water will actually be drawn out of the cell. So our arrows should be facing outward, okay? And that leads our cell to shrink a little bit, and also leads for a little bit more water in this outside area, okay? Okay. What might happen to the eggs if we leave them soaking overnight? They're gonna just be more extreme, but we need to use our vocabulary words. If this got so big that it burst, that's called lysis. If this got so small that it dried out, that's called crenation. Crenation. Okay, so the corn syrup egg will crenate and the distilled water egg will lysis. Thank you for joining me for this week's lab, and I will see you next week. Don't forget to use this lab report to take your quiz.